Okay, this is the board drawing. Now, I'm going to make a couple of assumptions. One is that you're a student in my fundamentals class. If you're not a student in the fundamentals class, then I'm assuming that you're one of my other students in one of the other refrigeration air conditioning classes, and you're accessing this on the educational blog site that I have for you. I guess you could be accessing this from someplace else, and you're welcome to it if you're not one of the students. If you're not, let me just say a couple things. This is a generalization, an overview of the mechanical vapor compression refrigeration cycle. I'm not going to get in real deep to the specifics, and I cover in one or two sentences in this series of videos that we've put together. I've got some deep subjects that I just make some very broad generalizations about. So if you're not in one of my classes, you really need to get to either one of my classes, or if you don't live in our school district, you need to get to the local technical vocational school that you have available. So once again, this is a very broad generalization. I'm not going to get into transcritical carbon dioxide systems. I'm not going to talk about auxiliary heat exchangers, any of those types. I'm not even going to get into the specifics of the metering devices themselves and how many there are. This is a very broad generalization of the mechanical vapor compression refrigeration cycle in this series of videos. All right, let's get started. Okay, this is the mechanical vapor compression refrigeration cycle. We start with the compressor. The compressor is the number one thing for me. I draw it with a heart in it because it is the heart of the system. The job of the compressor, a couple of things. Circulate refrigerant, and it causes a pressure differential on both sides of the system. Now remember, our compressor operates off of the two gas laws that we've talked about. We talked about Boyle's law. You remember Disco Boyle. As the volume goes down, pressure goes up. As the volume goes down, the pressure goes up. So Mr. Boyle's doing this kind of thing. And then we talked about touchdown Charlie. Remember? Pressure goes up, temperature goes up. Pressure goes down, temperature goes down. So what we do, we take in a low temperature pressure vapor, we lower the cylinder size, we raise the pressure, therefore raise the temperature. We send the refrigerant out as a high temperature, high pressure vapor. Technically, we don't pump liquid. We pump vapor through the compressor. We always pump vapor through a refrigerant compressor. It is the heart of the system. It's the first major component in our refrigeration system. We send the refrigerant through the discharge line, and then we'll go over to the next major component in our refrigeration system. Okay, the second major component in our refrigeration system is our condenser. Now the refrigerant comes through the discharge line into our condenser. The job of the condenser is to reject heat. That's all it does. It rejects heat. It does so through three processes. The first process that it goes through is to desuperheat. The definition of desuperheating is to remove heat from vapor. That's all that is. We bring the refrigerant down to its latent heat point of condensation. At this point, the refrigerant is in a state of saturation. Remember what I said about saturation? It's kind of like vapor and liquid that exist at the same time. Your mind's eye should kind of be seeing a real foggy day. You can barely see in front of your car because the fog is so bad. That's kind of what saturation is. It's vapor and liquid that exist at the same time. So we desuperheat the refrigerant, we bring it down to the point where it's going to condense, and this is what actually happens. This is the phase change. This is where the refrigerant is in a state of saturation and it condenses. So it changes to liquid here. Once we change to liquid, we're going to subcool the refrigerant. Subcooling is nothing more than removing heat from liquid. We subcool liquid, we desuperheat vapor, and in the second portion of this, we condense. So we desuperheat, condense, and subcool. We send the refrigerant through the outlet of the condenser. That's what my little X is for there. We may hit a liquid line receiver, we may not. It's not in every system. That's why it doesn't get its own number. It might be there, just it's a storage tank. That's all it is. So our second major component rejects heat. It is the condenser. Let's move on to our next major component. All right, we are now at the third major component of our mechanical vapor compression system. That's the metering device. I have this an MD there. Now I think your textbook calls it an expansion device. I call it a metering device. Either, either, neither, neither. Metering device. Metering device is an engineered restriction in the flow of refrigerant. It takes a little bit of the liquid in, it has a tiny, tiny little opening. It just kind of depends on what type of metering device. Again, we've talked about 7 of them when we go through that chapter. But it restricts the flow of refrigerant. When it comes out into the evaporator, we'll talk about that in a second, we're going from a real small space to a real big space. Let's go back to the gas laws that we talked about, Boyle's Law and Charles' Law. We remember when the space gets smaller, the pressure goes up. When the space gets bigger, the pressure goes down. And we remember from Charles' Law that if the pressure goes down, temperature goes down. So we come through the metering device, much bigger space in the evaporator coil, pressure goes down, temperature goes down. That's what the metering device does. It causes that pressure change. Remember, everything going back towards the condenser is a high pressure, high temperature. Once we get to the metering device, it restricts the flow, it pops out into the evaporator, and that's where we get our low temperature, low pressure. Also remember, at the outlet of this metering device, we're going to have what is called flash gas. Now, if you remember flash gas, probably the easiest explanation is just when liquid bypasses the saturation state and gets to be vapor. There's a little bit more to it than that. It's in the world of physics, and we're not physics guys, we're heating and air conditioning guys. So that's all we're really going to remember about flash gas. It's when the refrigerant changes state from a liquid to a vapor, it bypasses saturation. You'll remember going back from our theory of heat that saturation is where the majority of the heat is either absorbed or rejected. In this case, when we bypass saturation, we don't absorb quite as much heat. So we have our metering device, engineered restriction in the flow of refrigerant. It helps to cause a low pressure, low temperature condition inside the next major component. Let's go there next. All right, 4th major component in our refrigeration system is our evaporator. The job of the evaporator is to absorb heat. Now, remember, when we came out of the metering device, we were at a low temperature, low pressure. The engineers designed these things so that the majority of the coil is filled up with a saturated refrigerant. Granted, it's a low temperature, low pressure saturated refrigerant, but it's still in the state of saturation. Now, a couple of things we're going to talk about here. You will remember the definition that I gave you of refrigerant, any substance that as it changes state from a liquid to a vapor absorbs heat. Well, that's what's happening here. We're going to bring a heat-laden something, air, water, across the evaporator. We're going to absorb the heat out of the air or out of the water, and we're going to recirculate that. The refrigerant is going to absorb the heat. It's in the state of saturation. We call it its latent heat point of vaporization. This simply means that it's in a state of saturation. We're going to try and turn it into a vapor. So the majority of our coil is in a state of saturation. Now, depending upon what type of system, how it's engineered, it could be anywhere from 50% to 100% of a state of saturation. That's just a variable. We're going to get to some of that. The last little portions of the coil are used to superheat the refrigerant. Now, we remember that desuperheating over on the condenser side was removing heat from vapor. So on the evaporator side, where we superheat the refrigerant, that's heat added to vapor. That's all superheat is. It's adding heat to vapor. We'll get into the calculations of how you figure those things out. But our 4th major component absorbs heat. We absorb heat from boiling off the saturated liquid that's in here. We'll add some heat to the vapor. We call that superheat. We'll go back through the suction line. It's a low temperature, low pressure vapor line. There may or may not be an accumulator in here. It's not in every system. That's why it doesn't get its own number. The accumulator is nothing more than a surge tank. Some of the systems we're going to deal with are going to have some hot gas defrost or something like that, in which case we want to put an accumulator in there to catch any liquid that might start coming back towards the compressor. Remember, our compressors are vapor pumps. They don't do well trying to pump liquid. So an accumulator there is a protective device. That is it. We come out of the evaporator, head back to the compressor. Once we get back to the compressor, the cycle starts all over again. That is the mechanical vapor compression refrigeration cycle. That's it.